Hi everyone, we are excited to share how we improve our regressor for M3 final hackathon and how we optimize its accuracy and fit. Building a good model involves data processors, feature engineering, model selection, and hyperparameter tuning, but having a strong model isn't enough. It must also generate well to new data. We will cover two main areas: how we improve performance and how we evaluate accuracy and fit. First, we focus on data processing and cleaning. High quality data is key to a good model. We handle missing value by using median imputation for numbers and mode for or unknown for categories. Then we encode categorical variables using one-hot encoding for small categories and ordinal encoding when other method. We also scale numerical features with standard scalar to keep everything on the same scale, which improve model stability. Next, we work on feature engineering. We remove redundant feature by checking for high correlation to reduce complexity. We also create new features grouping latitude and longitude into beams for better generalization and developing a host density matrix to estimate demand to handle outliers. We apply log transformation to smooth screw distributions and capping extreme values to prevent them for distorting the model. For the model selection, we test linear regression, decision tree, and neural network. We choose a neural network because it learns complex patterns well. Our model had 4 layers with 5.2 to 5.6 and 1 to 8 neurons. With batch normalization to improve training stability and dropout layers. 0.3 and 0.2 to prevent overfitting. We use rectified-linear unit activation to introduce non-linearity and improve linear efficiency.
For optimal training, I use the Atom W optimizer with weight decay to achieve improved generalization. I also use the learning rate scheduler reduce error on plateau, which dynamically adjusts the learning rate when improvements plateaued. My batch size was 256 to maintain stable gradient updates. To prevent overfitting, I utilize earning stopping with patience 15 echoes. During training, I monitor loss and RMSE at each echo and ensure that my validation performance align with training. Now let's proceed to checking and enhancing the fit of my regressor. The performance of a model only makes sense if it is good at generalization to unseen data. For this purpose, I employed several techniques with evaluation. I first divided my dataset into training and validation sets based on an 80 to 20 split. This means that the model I learned from one set of the data while it was tested on another to avoid memorization. I also employed RMSE as my primary measure of evaluation later on. RMSE provides us with an interpretable measure of predictability that prefers smaller errors in a much greater manner. I also look at training loss versus validation loss plots. These, if plotted with epoch on the x-axis, told us whether the model overfit or underfit or not. When I observed my validation loss was plateauing, but training loss continued to fall, I inserted dropout layers and introduced regularization to combat overfitting. The most important role was played by hyperparameter optimization in order to boost my model's fit. I turned the learning rates, dropout rates, and the neurons in each layer to optimization performance. By doing so, I ensured that my training loss and validation loss came close together, which indicated good generalization. For further verification of my model, I conducted residual analysis. Residuals or discrepancy between actual and predicted values must be randomly scattered. If there is a pattern, it may mean a missing predictor or nonlinearity. By narrowing down my feature set and having a well-calibrated model, I avoided biases and enhanced predictive accuracy. Finally, I evaluated my best performing model on ANSI test data. I stored the best model by validation loss and used it to make final price predictions. Since I had done a log transformation to normalize distributions of price, I reversed this with NP-EXM1 before storing the final predictions as predictions.csv. In short, I improved the performance of our regressor by cleaning and processing data, feature engineering with informative features, selecting a best neural network model, and hyperparameter tuning. To compare and optimize the model, I monitor RMSE cross-validated on-chain test splits and performed residual analysis. While my model was precise, there's always room for improvement. In the future, we will explore other architectures such as transformers for tabular data, employee automated feature selection techniques, and employee insensible learning to achieve even better performance. Thank you for listening.